Okay, briefly, member-wise copy, where we inspect what happens to stack and pointer variables when a class is copied into another class, thus creating a second class. We'll talk about class dynamic memory issues. That'll be like two classes created, both pointing to the same memory, how we fix that issue. Our AII resource acquisition is initialization. We are shooting for creating a class. Behind the scenes, we are creating dynamic memory for that class, kind of like the vector and the string class. And then we will look at the counterpart to the constructor, which is a destructor. So remember, constructor helps us initialize variables or create memory, and the destructor will help us clear memory. Okay, so let's get to it. Okay, so we start with the header guard. So if not defined my vector, then go ahead and define my vector. Okay, and we create a simple class. We'll name it vector. Notice it's a capital V, right? The C++ vector has a lowercase v. Okay. So we want to create some what does that include? I don't remember that include, but let me check here. Yeah, so this will be the last homework this week for the tic-tac-toe. So pretty sure some of you are happy that's the case, but I always feel that students should be exposed to what they would be exposed out there in the real world, right? As opposed to like just creating simple homeworks to give you false confidence, right? So let's just throw you out there and then, you know, you go ahead and tackle it and hopefully learn more like that. Okay, this one. Okay, so we'll say private data size of t size. Okay, so envision trying to look into the real standard library vector. We know we have somehow in the class they're keeping tabs of the size. So to do that, first thing they need is to create a size data type, right? And size t, remember, it's a data type that only holds positive numbers, and it can hold like twice the value of an integer. Okay, so a very large number. We'll go ahead and say, okay, we need a constructor that accepts the size, and we will initialize our local size with the incoming s value. Okay, and just like our standard library vector, we need a way to query the size of the vector. So when we just say, well, let's create a size function that's const, and it simply returns size. Again, we don't need any CPP code right now. This is a one statement line. And for the constructor, so far we don't need anything, okay? So let's inspect that member-wise copy. We will need a test case for this. And always remember, we need to include the header, and after that we can start using, right? So test vector size function. Y for member-wise copy. Okay. So we create vector of 3 elements, and then we say create another vector v1, but from v. So create a copy of it. Okay, and then we create our assertion v dot size. Okay, so we want to inspect what happens when to the private data. Okay, let's walk through this code before I run it. Vector of v3 finds a constructor. S is 3. This statement says initialize size with the value of s. It is an initializer list, so then size should be 3. Okay, now what we are testing for is, will this value of size be copied from v to v1's private data? Okay, and once we run it, then we'll know what happens. So let's go ahead and run that test case. Okay, so while that's running, we can diagram to see what's happening. And we'll copy this code, paste it in here. Okay. So for now, we are not using this part of the memory. Okay, so we know size will be here with the value 3, and then we want to inspect what happens there. Okay, so let's see if our test case has finished executing. Almost. So green, up arrow, space, /s, enter. So notice 3 equals 3. So from here we can conclude, oh, okay, so it does copy the value from private v size to v1 size. Okay, so we can agree with this, that happens. Okay, so so they are copied. We can conclude that. Okay, so now we go back into our vector. Now what we're trying to do is, how did those guys, the C++ developers, how did they create the vector? So recall, I've always stated, and I've drawn several diagrams where I explain that the vector data is on the heap, which means that we need to create some dynamic memory here for this vector class. And we can do that by creating a pointer to integer, and we name these elements. Remember the relationship between a pointer and an array. An array's name is simply the first address to the list. So knowing that, we can say, okay, so I want a pointer to elements, meaning, well, I know the pointer can point somewhere to an address, and an array's list is an address, so then from there I can, within my class, I can know where my list is. Okay, we will have to move this code into the CPP for now, well, permanently. Let me go to CPP. Vector size t. Okay. So again, this is an initializer list, okay? We can initialize more than one variable by separating them with commas. So we know we have the size, and now we want to say elements, initialize it with new integer array of s, which is 3, right, in our case. So before I go and write code, let's so it's the same code, and we have this code. We won't be able to map all of it for now, but I'll still prepare the diagrams. Okay, so we have heap in play and stack in play. So we know size will be 3, and then we need a space for the elements dynamic memory, okay? And assuming this is like 96, 92, 88, 4. Let's assume we get this spots. So then elements will be y96, meaning find your first element at address y96, okay? And then we want to know what happens here, right? So for sure we know that we will get size. Like that one we should know because we've already ran the test case, right? So we know 3 is going to be copied. It's going to be copied for us. And then we need another block for elements of v1. So that's what we're trying to see what happens. Okay, so let me go back over here, and what we will do is I'm going to include IOStream so that we can output statements so that we can see which constructor is running. Okay, for now there's only one, but as our program grows we will have more than one. So we'll say cout we'll say constructor with this. That way we know it's the one with one parameter, okay? And then we will say create memory. And then we will say let me display the address, and I know that elements is a pointer, so just by saying elements I can display the address, okay? And then a new line. Okay, and then we go to our test case, and we want to test the pointer copy. It's going to be the exact same test case, but we'll add something. Well, actually this is going to change. Okay, so we create a vector with 3 elements, and then we create a copy of that vector, and then we'll purposely say okay, let me write some code to change vector element of 0 to 5. Obvious error here. It's like no operator matches this operands, meaning we've not written any code for our class to support using the subscript operators. But we learned about operator overloading, so we need to write some code for that so that that piece of code can work for us. And then we say, okay, so let's do that. I'll return a reference to an integer, operator, subscript, size of t, size, or I, sorry, not t, I, the index. And then we say, okay, return elements at I. The key part here is the reference. So if we have an array in memory, this one, when we say reference, we're like return the address for that element, and then we'll be able to modify it, right? So if we go back and look at this code here, when we say v of 0, then we're saying give me the address of the 0th element, and then I'm going to change the value to 5. Okay, so we're asking, hey, give me this address, and then we go in and modify the value. Okay, that's one part. We also need a way to read, right? So that piece of the code, since there's no const, we're like, oh, okay, we want it available for writing, and we write code that also returns a reference to the operator, overload the subscript operator, size of I, const, and then we simply return the element at I. Okay, by adding this code, now our code works, you see. V of 0 equals 5, right? Actually, this was the first overload I created. And then to use the second overload, we can say, okay, require that V of 0 not equal to V of 1. And if you're having problems following along, I'll complete the diagram in a little bit, okay? Actually, right, so we're assuming that when we say v1 equals v, v1 is going to have 3 elements somewhere here. So we want to compare the first element of v to the first element of v1, okay? They should not be equal. Why? Because there's 2 different memory regions, okay? So let's see what happens. Semicolon here. And let me run it. Okay, so it's building. And notice it failed, meaning what? So if we look at the output, notice that we have create memory, but then something weird happens, right? If this is the case, then this is what should happen, right? So we're here and we're like, okay, so it says create memory, meaning I did get more slots. Okay, assuming it gave us those 3 slots, so then it gave us these slots. So then this would be Y80. That's what should be happening. But let me go ahead and erase this and erase that. According to our, and this is 5, right? Because I changed the value to 5. Create a vector v3. Here, 3 elements. v1 equals v. We saw from the output that some memory was created for v1 here. But why is the test case failing? So let's see. V of 0, right? V of 0. So this is element 0 from vector, okay, from V. This one is different memory region, but it's saying here V1 of 0 is also equal 5, right? Because if they were not equal, then our test case will be passing, but as we can see from the output, there's 5 and 5, so what's actually happening is this guy is also pointing to Y96. And then we have like some memory here that's what's that? Anyone? It's some type of memory issue, but what is it? It's a memory leak, right? Because how will we are going to free this memory if our pointer's not pointing to it, right? So when we delete this memory, now this guy's going to be a dangling pointer, and then if this guy tries to delete that memory or use it, it may get lucky if the values haven't been overwritten and work for a little bit, but eventually we will run into problems, right? So we need to fix this issue, right? So yeah, this is a memory leak, and of course that's not good, right? So then we come back over here and we can take care of it with the concept of a copy constructor. And in that constructor we write some code to take care of that issue. So we say, okay, vector const reference to vector copy constructor. This will be rule 1 of 3 from the rule of 3, which means that anytime you use dynamic memory, you need to implement the rule of 3. We'll cover them today, okay? Copy constructor, copy assignment, and destructor. Obviously, destructor clears memory. Copy constructor takes care of this issue where the member-wise copy, C++, trying to be helpful to us, changes where the V1 pointer is pointing to. Now they're both pointing to V. We got to fix that issue, okay, and have it point to its regular memory, okay? So let's take care of that. Okay, so notice C++, it didn't really do anything wrong. It was us because of the way C++ works, right? And that's why C++ is such a great compiler for teaching memory management concepts. If the copy constructor is not around, then C++ will use the default constructor and then we revert to member-wise copy to try to to try to rectify or to make this work. Okay, this piece right here. Obviously, we just saw that with pointers it doesn't work, so we need to help C++ out. So that's what we are shooting for. So we go and let's implement the copy constructor. So we make it part of our class, and we wanna, number one, initialize size for v1, initialize memory for v1, and finally copy element values from v to v1. Okay, that's what we are shooting for. Okay, so how do we do that? Well, we have our initializer list, and we do step one, initialize size for v1. Even though we know we get the free member-wise copy, we want to take control of that ourselves. So we're like, okay, get the size from v. Okay, and then we're like, okay, I want to initialize the memory for my private data elements, and I want to say a new memory of v.size. So I've done step one and step two. Okay, initialize size for v1, initialize memory for v1, and then step three is copy element values from v to v1. Okay, so and then we first we write this statement. Okay, so we can see what's executing. Execute copy constructor, and then we're like, okay, for start size of t, I equals 0, I less than v dot size increment I, and then we copy into elements of I each element from v dot elements of I, right? So we come back to our diagram. We want to copy the values one at a time to a newly created memory. Okay, that's what this is doing. And hopefully once we do this, then we eliminate this issue. Okay, so I will execute this test case and start running, writing the new diagram. Okay, so we come back over here. Okay, it's the same code. And okay, okay, so we know size 3, and then elements, I think it was here 96, right? So assuming this is y, okay, y 96, and then we know size will be copied, and then we have elements. Okay, where did I map them to 80? Did I mess up my numbering? 80, 76, 72. Okay. So assuming we got these 3 slots, okay? So then this would be Y80. Okay. And what is there? We don't know yet, right? We're creating, getting memory, but we don't know what values were there. So we'll take care of that issue in a little bit. Whatever value was there last, that's what's currently there. Okay, so let's see what happened here. So we have 1, 2, so we'll focus on this ones, right? Because the first 2 are for the first example. But notice now we say create memory and then execute copy constructor. Maybe here I also display the memory. Elements. When we see that weird hex, we'll know that that's the address, okay? So let's run it. So in Legacy C++, before smart pointers, a lot of classes that were going to use dynamic memory had to make sure they implemented the rule of 3 before you could even start writing code for the class. You were just taking care of memory. Okay, so this was the test case number 1. We're focused on test case number 2, but notice memory is created at 17630 and then at 70D8. But the important part is that now it's passing, but let's inspect the details. Right, so 5 is not equal to some large number, right? And that was what I was talking about. Well, what's here? We don't know. Whatever value was there last, that's what is going to be there. We purposely initialized this one to 5, so that one is 5, okay? So everything good, meaning it's pointing to its correct memory pointer. Why? Because our code ran. Notice if we go back, let me see if I can scroll back up a little bit. So initially, like a constructor ran, let me see. Well, you know what? Instead of trying to go find it, let me revert back to the issue, right? So I'll comment this out, and then I will purposely also for temporarily comment this out, and I'll make our test case fail again. So we go here and we execute just to see, well, what was happening before that our test case was failing, but now like we added this copy constructor and the code's magically working now. Okay, it's still building. Okay, so the constructor was executing 2 times. Okay, so that's where I was saying, like, if this is not available, C++ runs a constructor where new memory is created, but then it does a member-wise copy for stack and pointers, and that's why the pointers get pointing to the first class's memory. But if we write our code to fix that issue, now we are like, no, want to make sure that that doesn't happen. So then we have to initialize size, initialize memory for V1, and then copy elements from V to V1. And once that happens, then this scenario is occurring to where both classes have their own memory and both of them are pointing correctly to their own memory. So that's why our test case passes, because I modified the first list and then now this one's pointing correctly to its own list instead of pointing to this list like before. Okay, so that's the issue we took care of right now, and we should see a passing test case. I think the book briefly talks about the rule of 3, but I always want to make sure that I go through an elaborate example of developing a class that uses dynamic memory, so that if in the future you encounter C++, then you'll be able to tackle it. But then also it also helps you understand like how Java and C# and Python are working. So notice now the constructor executes for the first V, and then for V1 the copy constructor executes. This is the first test case. This is the second test case. But notice now our code's executing the copy constructor, and notice all of them have their own memory, which is what we're after. Okay, and all of them are pointing to their own correct memory. That's why our test case passes now. Okay, let's explore another issue that we'll face, and test overriding an existing class with a copy. Okay, so meaning we say, okay, let me create a vector of 3. Let me create a vector of 3. But now let me override an existing class V1 with V. Okay, so that's what we are looking to tackle. We want to see, well, what happens here. Okay, and we can do the same thing. We can say, okay, V of 0 equals 5, and then we can say, okay, so let's write our assertion. V of 0 should not be equal to V1 of 0 after we run that statement on 41. Okay, so let's go diagram that. Yep. Okay. Okay, so let me copy this code. Okay, and let's start diagramming this. Okay, so we're like, okay, stack heap okay, okay, and we know the drill now, so we know that size, and then we know we need room for elements. We'll keep the same locations. Okay, actually, before I finish this off, we should go here and take care of that issue where we got that weird large number, right? So after we create the memory, we should initialize all the element elements to 0. So we say I dot listen size plus plus I elements at I equal 0. Okay, so now we can, instead of putting question marks, we can say, well, all of this initially are 0. Okay, and this one, assuming that's Y, so Y96. And then this one, size elements. So this is 3, and we know that some memory is created, and it should be pointing there. Okay, and then this should be Y80. Let's go back to our test case. I didn't run it, right? Or run. So we're going to see that we're going to run into that same issue where the pointers are out of order. So we're going to have to write code to fix that. So why is it happening like that? Well, I mean, because we're telling C++, hey, I'm going to take care of managing memory for this class. And C++ will let us. We just have to make sure that we are writing the memory management rule of 3 code to handle memory properly. Okay. Notice I've not even begun to talk about writing code to make the vector work. Right now we're writing code just to take care of memory issues. Okay. So let's inspect what happened to our guy. Okay, so we are looking at let me make this larger. I should have written a new line, right? Just to make sure. Okay, so 1 2 1 2, and notice again our constructor's firing twice, and we know from the previous example that, well, that's good, but C++ is getting the pointers confused again, or I mean, it's trying to help us, but this is not the case. This isn't happening. This isn't pointing to this. Instead, it's again pointing over here. So this is Y96. Okay, so we have to fix that issue. That's what's happening. And again, we have this memory leak because we will not be able to clear that memory anymore. The pointer is gone from it, so we have to take care of that situation. Also, we're creating memory dynamically here, but we're not deleting it anywhere. So we'll take care of that issue with the third rule of 3, which is a destructor. Okay, so we'll get there. But for now, we need to write the second rule from the rule of 3, and that's the copy assignment. And in the copy assignment, we take care of this issue that we see here. Okay, so we overwrite. We write code, to overwrite the equals operator. So we turn a reference, and then we say operator equals, and then we take a const vector reference, and we write code for that. And we'll list what we have to do. Okay, let me make sure that this error is gone. So we need to make it part of our vector class, and we do there. Okay, so number 1, we need to create temporary memory. Number 2, we need to copy values from V into temporary memory. Okay, so create memory. Let's be explicit, right? For V1. Okay, number 3, delete V1 element memory. Number 4, point elements memory to temporary memory. And number 5, return a reference to this vector. Okay. So also now you can begin to appreciate the unique pointers, right? They take care of all of this for you. Like, we just started using them. We don't have to worry about any of these issues. Okay, so create temporary memory for V1. Okay, let's also display what's happening, okay? So copy assignment operator, and we'll also actually this will be the last statement, okay? I'll type the statement before that right now. So let me see, elements. And that one has to be somewhere there. Okay, so now we say, okay, step 1, create temporary memory for V1. Okay, pointer temp equals new int v.size. So that's step 1, create temporary memory. Copy values from V into temporary memory V1. Okay, for size of ti equals 0, I less than v.size. Okay, so copy values from V into temporary memory. So temp of I equals v.elements at I. Step 3, delete V1 elements memory. Which memory? This one right here. Remember the memory leak? So we're deleting that one. So delete elements. So meaning actually I'm okay here. Elements equals temp now, right? So number 4 is point elements to temporary memory. So elements equal to temp. So now that's where I put my statement to get the correct address for the elements. And then return a reference to this vector. But also let's get size equals v.size, since we're taking control of making all the copies ourselves. And then we say return the dereference pointer. Okay, once we do this, then we should be okay. But before we run it, let's go ahead and map this. Let me copy the code. It's the same code. Okay. Okay. Okay, so we know size, elements. So I'm hoping the diagrams like help you create a very good picture of what's going on. Okay, and if it doesn't immediately, maybe after watching the videos, then it does, right? So then Y96. Or if you're like me, sometime later it's kind of like, oh, that's what they were saying. Okay, so then size, elements. So assuming there was here, right? I'm just making this up. And that's what we're shooting for. Y80, but we know that this one was over here, but we're going to fix that with our code. Okay, and then finally we have one more. So magically they landed here. Okay, so this is the temp memory that's happening when we're saying v1 equals v. Okay, so we're saying, okay, create temp memory, copy value. So we copy value 000, and then we're saying, okay, delete the memory. So once we delete the memory, we're like, okay, so delete the memory. This memory is available for use by our program now. And then we're saying that now we want to point to the new memory. So we point to the new memory like that. And why are we doing all this? To avoid this situation, okay, where our pointers get lost. So we have to go through all this mechanics to make sure that we don't get into that issue where we're leaking memory. This one's pointing over here, so now we're like, okay, you have your own memory, be happy. I've created memory for you. I've moved values from your old memory here, and I've deleted your old memory, so everything should work now as intended. So we go back into our test case, and no, initially when we ran this, our code broke, right? So let me just verify that. Yeah, so now our code should be okay. So we come here, we've made the change in we've added the copy assignment, we come in here, run in terminal, we should be okay. And why is it like this? Well, that's the way it's going to be if we want to control memory. We have to be aware of all these rules and all these possible gotchas and, you know, obstacles that we'll run into. So we have to write this code. Okay. Taking this time. So any questions? You all happy? This was left toward the end of the semester. So notice now our copy assignment operator is executing, and our so let me see, 1, 2, those were the first two, 1, 2, second test case, third test case right here. So notice the constructor runs regardless. And it creates the memory, it creates this memory. But then the pointer points over here, right? And it ends up like this, where we have a memory leak and two classes pointing to the same memory. So then we have to go back and look at this, right? So now once the copy assignment operator executes, then we copy values over here to actually first create this memory, temp, copy values, delete memory, have this point to the new memory, and now we're good. Okay, we don't get into the situation where it was like this, right? Oops, I wanted to do that. Okay, we don't get into that situation. all along this is what we wanted, but we were running into issues. So before we were left out in the cold, we're like, no, let's take control of the situation and make it right. So notice now the end is you are here, and you are not pointing to 80, you are pointing to 60. And now we don't have any memory leaks, and now both have their own class dynamic memory, and we're good. And we can see that our test case now is good, right? Meaning this changed to 5, but this didn't, right? So we're okay. Now both have their own memory to work with, which is good. All this, the unique pointers and the smart pointers, they take care for us. So does the string and the vector, right? And hopefully you get a very good appreciation for the C++ developers, right? The ones who created the GCC and the Clang compiler, they had to implement the vector, right? Obviously, they're expert C++ programmers, right? Like I'm just showing you how they might have done it, right? Okay, so this was copy assignment rule 2 of 3 from the rule of 3. Oops, the rule of 3 for legacy C++. Okay, so as I was saying earlier, we are allocating memory and we are using it, but we are not releasing it. But that's okay, right? I was gonna get to it. I mean, there's a memory leak here, but we can take care of it. So remember, create memory, use memory, free memory. We go back here, we have the constructor, and we have another constructor here. And the counterpart for that is a destructor. And that one, just like the constructor, executes when the class is going out of scope or being released from memory. So once a class is being released from memory, whatever code we put into the vector destructor will execute. And this is where we want to put the code to clean up memory, okay? So let's make it part of our class. Clear, delete, free memory, whatever you want to call it. That's what's going on there. And then we have to say delete elements. So we free the memory. So assuming this was some function, right? Like void some function. Once the function would start exiting here, then the destructor for v1 would execute, and then the destructor for v would execute, and thus cleaning out this memory and then clearing out this memory, okay? That's what we need to show. Okay, so let's see. So no questions yet. Okay, so how do we show that though? How can we show that happening? Well, we can run the test cases and see if we see clear delete free memory statements. So let's do that. So again, let's go inspect the test case code. Remember how C++ stack variables work. The test case for this test case activation frame for this will be loaded onto memory, and there'll be region for this, right? Memory addresses for those. But once the function starts executing, the memory for this function will start clearing out. That's when v and v1 are starting to go out of scope, and C++ behind the scenes, since we've written code, we'll see that we have a destructor, and C++ will be like, oh, let me call it destructor, and the memory should be released. Okay, so that's why I'm running the test cases. So what is the rule of three? The rule of three means that any time you have a class that uses dynamic memory, you need a copy constructor, a copy assignment, and a destructor to manage memory properly. Okay, that should be the case, yeah. Yeah, for last in, first out. Okay, so and we can show that by before we call delete by displaying the memory, right? So we can say elements. Okay. And we'll have to wait for it to execute. Let me see if I can come back here. Terminal. We're looking for delete, okay? Or clear free memory statements. Okay, so create memory, clear memory, clear memory. So 2 and 2. Create memory, clear memory, clear memory. Create memory. Remember this 2 right here, they work together, right? Because we ourselves are taking control of cleaning out this memory and instead using this memory, okay? So we will not see 3 clear memories over here. We'll see 2 because in our code here, we deleted memory ourselves, okay? So that's why you won't see 3 and 3 like over here we had 2 and 2. So that's the case, okay? So let me see here. So create memory, execute copy constructor, clear, delete, free memory. Okay, right? So notice last in, first out, right? So, and then let me see down here. We have create memory, and then we're good too, right? So last in, first out. So C++ clearing out the last memory that was loaded, right? But how is this working though? Like, do you all understand what I'm saying here? That this is loaded on, this whole code right here is loaded onto the stack. Boom. Like the main memory or those activation records we worked on, it's on the stack. And while test case is running, B and B1 are in memory. Test case starts exiting, it starts cleaning out after itself, right? B1 out, B out, okay? So we didn't have to do anything. All we had to do was follow this rule of three concept, mainly the destructor piece, to make sure that memory is released. But let's put it into a smaller scope, right? Because those test cases, they can be confusing. So let's go into main. And not actually into main, here. And I'm gonna write some free functions. Okay, so I'm like, okay, void use stack vector, okay, vector CPP. Again, this is a free function, okay. And what does use stack vector mean? It simply means that I'm going to create a vector here, v, and that's it. Like, I'm using it. Just the fact that I created it, I'm using it. And then we'll run this in main, and we'll see that the same thing's going to happen. The vector is going to be loaded onto memory, and then we'll eventually see the clear memory output, meaning C++, the fact that we're using this struct right here, the structure, we're limiting the vector into this function. Once this function is removed from memory, the vector dynamic memory will also be removed from memory. So let's see, run in terminal. And well, obviously, if I don't put anything in main, nothing happens, right? So let me see, is this the right one? 9, yep. Include vector.h, and then here I can say use stack vector. And now we should be able to see something. So notice, create memory, clear memory. But what is happening, right? So let's inspect that a little further. Cout. So we'll say here cout before function executes. And then we'll say after function executes. And let's run it again. So notice, before function executes or is loaded onto the stack, it's loaded onto the stack, it creates the memory, and then notice clear delete free memory is displayed, and then finally the function has executed, right? So everything happens as I was describing. Once that function starts being unloaded from the stack, then the destructor is executed and our memory is freed, and that's what we want, right? So we're not creating a memory leak, okay? And then finally, one more example to show you that we can run into issues too. So we'll create a heap vector. Not to be confused with the memory that's elements that's on the heap. Here, those elements are on the heap. Here, they're also on the heap, okay? But when I say create a heap vector, I'm creating a pointer to a vector, and I'm saying create a new vector of size 3, right? So I'm creating a dynamic memory. And let's see what happens, okay? So I go to main, and then we'll do the same exercise with the exception that this will be use heap vector. Okay, so go ahead and run it. Before function executes, create memory. But nowhere, even after function executes, do I see clear, delete, or free memory. Why? Anyone? Can anyone tell me? Because the vector is on the stack, or meaning the vector is on the heap? Right. So this statement, anytime you're creating memory dynamically, even though here we're creating memory dynamically and we're cleaning up, but that's within the class, okay? Oops, sorry, here within the class. Over here, we're like, okay, so I want to create a dynamic instance of vector. If we do that, then we have to make sure we call delete. So theoretically, we would use the vector, right? Somewhere here we would use it, and then finally, we would have to explicitly clear memory. So let me go ahead and execute this again. which one of these two methods is preferred? Obviously this one, because we are using C++ constructs and the C++ programming language to help us manage when the memory is released. Here we are again saying, hey, I know, I mean, thank you, but I'm just going to take control. But the way we've written our code, we should always shoot to use the code for vector. We should use shoot to use this one. And notice now, before function executes, create memory, we call delete, clear delete free memory. We delete the memory, and after function executes. So notice that we don't call delete. We've in essence created a memory leak, which is not what we want to do, right? So this was the first lecture of memory management for classes. We'll continue in the next class, in the next few lectures, exploring memory and classes while we continue to develop this vector class, right? Eventually, we'll have a basic vector that allows users of the vector to create a list and add items to the list. And if the list, if there's too many pushbacks, we'll grab a new chunk of memory from somewhere else, copy into that new memory, and grant them more memory, right? So we'll do a lot of that. Yeah, this is what the smart pointers are doing, and it's a lot of boilerplate code. But if you wanted to take control of dynamic memory properly, then this is the way to do it, and this is still in use today. We'll expand to the rule of 5 next week, where we explore more issues and we add more constructors and assignment operators to take care of issues. And finally, we'll have a full vector class that only manages memory properly, and then we'll continue adding some vector functionality later. Okay, so that's all I